So let me start with the presentation. Today the seminar is given by, is going to be lectured by Dr. Moise Bonilla. He has graduated in the University Iberoamericana, which is a private university here in the barrio of Mexico City. And he has got a PhD in Frankfurt in Germany. At present time he has, his formation has been in physics. His specialty is in quantum mechanics. And at present time he is a postdoc researcher in our Automatic Control department. So, Moise, thank you very much for participating.
First of all, thank you to Professor Guillermo for having invited me to give this interesting presentation. Well, I hope it will be informative for all of you. And basically, we are in 2025, and as you may have heard in the media, in the news, etc., this year was declared by UNESCO as the centenary of quantum mechanics. Why? Because 100 years ago, July the 29th, Heisenberg published a paper that gave the foundation for quantum mechanics. That's why it's called the centenary of quantum mechanics. And given that we are in this centenary, then there is a good question: what is the quantum computing about? Because you hear about quantum computing a lot in the media, in the TV shows, in the movies, etc. Also in some journals. So now the question that we will ask is, what is it and why is it important? So let's first start with the first question: why is it important? When you try to convince someone that your research is important, it's not enough to say because it's interesting. There are many things that are interesting. Hobbies are interesting, and not because of that I will do research about hobbies. But what is an objective answer is the money, the investment. The amount of investment that a topic draws is equals the importance. So as you can see, I always like to show to my students in 2024 the amount of money that was invested by developed countries about quantum engineering, namely quantum computing, quantum communications, etc. And as you may see, you can see there are lots and lots of figures, billions of dollars by China, Germany, United Kingdom, United States, etc. So let's go to a map, maybe it's more visual. And as you can see, basically all the developed countries are the big players in the investment on quantum computing. This investment translates into many things. One, for instance, tax-free for companies that are developing quantum technologies as quantum processors, etc. Also the creation of new journals just specialized on this topic, like for instance in the IEEE there is a recent journal called Transactions on Quantum Engineering. So it's very unusual that there is a new journal created just because of one topic. Or for instance there are creations of postgraduate programs, as for instance in ETH in Switzerland, Depto in the Netherlands, or for instance in the University of Sydney, etc. So there is a lot of investment and goodwill of the governments to encourage this quantum computing. So politically speaking, it is interesting because of the investments, because of the money, right? And in Latin America, well, Brazil is the one that is making laws just because of that, right? Now, having said that, the question is, what are the problems that quantum computing treats, right? So basically, I like to summarize it in 5 main categories, and all these categories have a common future. We will see that. So for instance, in logistics, quantum computing helps to find the best scenario. Quantum chemistry is the search of minimal molecular configuration. Cryptography is the search for a cryptographic key. Database is the search for a marked object. And machine learning is the search for the best fit. And as you can see, here there is a common word in all these 5 categories. Search, 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 search. Quantum computing, long story short, is techniques to find in an effective way something in a database. So all the problems in quantum computing are search problems. And all these problems are different problems because they are different search problems. And that's it. And most algorithms in quantum computing can be reduced to search problems. Okay? That's like the first thing to understand. Now we go to another question. What are the advantages? We have already classical computing and it works pretty well. I mean, I have cell phones, I can see YouTube. So it's going pretty well. But then, what's the big advantages of quantum computing? There are basically 2. The first one is the hardware. In classical logic, if you remember, classical logic is irreversible logic. What does that mean? For instance, consider this gate, and if I have a 0 on the output, you will never know what was the input. It might be 0, 0, 0, 1, or 1, 0, but you cannot reconstruct the input from the output. Okay, that's in a very simplified version, the concept of irreversible gates, right? And then from physics, that means, if we cannot reconstruct the input from the output, that means that there is a loss of information. And in physics, we know that a loss of information translates into an increase of entropy. And the increase of entropy implies the production of heat. Now you say, okay, that heat is very, very small. Yes, it is a delta, okay, it's small. But if you consider how many transistors and how many gates, for instance, a cell phone has, then you will start adding up all these deltas, and then at the end you have a great amount of heat. That's like, broadly speaking, why the computing hardware gets heated. Okay? On the other hand, in quantum logic, the quantum logic is reversible, because as we will see, all the manipulations on qubits are associated to invertible matrices. So since we have invertible matrices for every logic gate, then we can reconstruct the output from the input and the input from the output. Okay? So there is no loss of information, there is no increase in entropy, there is no dissipated heat. That's the first advantage. One of the promises is that quantum computers will not get hot. Okay? At least not hotter than the classical ones. The second advantage, as we already saw in the previous slides, is basically the search problems. Take for instance, in classical computing, you want to find this register, right? Just because you want. And then you have a database and you have a list of items, and then the question is, how do you find this register, this particular register in this database? So basically you will start just looking item by item by item, and then you will ask, is this the one I want? No. Okay, next one. Is this the one I want? No, next one. And then you might perform a more or less sophisticated strategy to choose the sample. Maybe you will go from the beginning to the end, or maybe you will start considering items from this part and then the other part, etc. So there are strategies, but at the end you will start looking item by item, right? And that's how you would find this register. In quantum computing, you will consider all the database, you will perform some computations, and then you will have peaks of probability, considering simultaneously all the registers. Right? So that's one of the main differences. Here you go one task at a time. In quantum computing, basically you consider all the database at once, and then you will have peaks. And this peak will locate in the item that I am searching. Right? For instance, in this case, this research was about particle physics, like the CERN, because they handle tons of information in databases, and they want to find a very specific atomic configuration, nuclear configuration. Right? So those are the, broadly speaking, the two main advantages of quantum computing. No heat, a more performant database. And now that we are talking about quantum computing, the first question is, okay, let's talk about the quantum bit. The quantum bit is the same as the classical bit. Let's see. For instance, in the classical bit, we can think of the classical bit as a coin on the floor, right? You have tails and heads. That's it. And then when you toss a coin and then it's on the floor, then it's either heads, it's either tails. You have two different states, right? And then you make an assignation. Heads will be 0, tails will be 1, two different states. And more importantly, once I have tossed the coin and it falls on the ground, then it's either heads, and if I toss it again, then it might be tails or heads, but at one particular time you will have always a well-defined state. It cannot be whatever thing, it's either heads or it's either tails. And I can go away 1 month and then I come back and it's the same result, okay? In the case of the quantum world, many people always ask me, okay, what is quantum mechanics? Because we have first to define what is quantum mechanics before we go to quantum computing, right? Because it has two words, quantum computing. In a very summarized way, in the words of Bohr, who was one of the first conceptual founders of quantum mechanics, he describes very, very well what is quantum mechanics in 2 lines. Quantum mechanics is a formalism, or a tool for deriving predictions of definite or statistical characters as regards information obtainable under experimental conditions described in classical terms. In other words, I have a microscopic system, and the only thing that I can describe from this atomic system are statistics, probabilities. Okay? So, for instance, if I have my atom, I don't know in what energy does it has, but I can know the statistics that it will describe, right? It's like the students. When a student starts in my lecture, I don't know what mark they will get, but there will be statistics, no? Maybe it might be 100% of the mark, 90% of the students, and the other 10% maybe 8, right? It's just the only thing that we can say about the quantum systems are just the statistics associated to it. Having said that, a quantum bit is just a coin on the air. When you toss a coin, and I ask you, is it heads or tails? There is no sense on that question because it's still flipping on the air. So I cannot say it's heads or tails. But either way, I have to say something about the system. I cannot say if it's heads or tails, but I can say if the coin has 60% probability of heads and 40% probability, 60% of probability of tails and 40% of probability of heads. Or maybe it's a fair coin and then it's a 50-50, right? That I can say. I can say basically, I can describe the probabilities of the results in this coin, but I cannot say what will be heads or tails. It will always be unknown. I have to wait until it falls on the ground, and then I say, okay, it's heads or it's tails. But on the air, I can just describe probabilities. And that's basically a quantum bit. You have two states, it's the same coin, you have two states. You have also the same assignation, heads are 0, tails are 1, but I cannot say if my quantum bit will be 0 or 1. What I can say is the probability, and that's the definite part of the quantum bit. In classical, you manipulate the bits 0 and 1. For instance, the NOT gate will take 0 and turn it into 1. You will take 1 and you will turn it into 0. Here, you cannot manipulate 0 and 1 because it's always unknown. But what you can manipulate is the probability, right? And that's what we will see about quantum computing. Okay, we just manipulate probabilities, not the states themselves. questions? But we can, sorry, the questions are exactly that. Okay. Aha. And then mathematically we have this quantum bit is basically equivalent to an event probability table, right? So we have two states, 0 and 1, with the corresponding probabilities. And the translation of this table is this mathematical equation in quantum mechanics. What is called the quantum state, you will hear about quantum state all the time when you open a book about quantum mechanics and quantum computing. The quantum state describes this table, namely the experimental preparation of the system. All the microscopic systems are described by events and probabilities. That's the only thing we can say about the microscopic world. And the quantum state side, it's only the mathematical translation of this kind of tables. Okay? So in this case, just as it is a convention, to describe this table, we write it in this way. The sign, the operation plus, means the union of events. So that means that my quantum bit, my quantum bit is prepared in such a way that we might have the event 0 or we might have the event 1. So the addition is a union of events. And these states are events. Okay? These coefficients here, if you take the square, the squared modulus, you will get a probability. Okay? So that's the basic recipe to translate experimental information into mathematical equations in quantum mechanics. It's very easy. Okay? Now, let's be a little bit more specific. In the case of the processors, there are like 6 types of processors, for instance, nowadays. The most intuitive one is the NMR processor. NMR stands for nuclear magnetic resonance. If you have gone to the hospital to get a tomography, and then you lie down and there is like a white, huge tube, and then you get inserted, well, that's an NMR tomography. And the NMR processor for quantum computing is that huge thing, but miniaturized in this size, like a microwave in this kind of size. So in this case, we manipulate nuclei from molecules, and the nuclei from molecules have magnetic states. And then you put a test tube with a liquid, let's say chloroform, water, etc. Then you put a coil in the vertical direction. You apply a magnetic field, V0, and then these nuclei can either be parallel to the main magnetic field or antiparallel to the magnetic field. And then you assign this physical state to 0 and physical state to 1. That's it. Or you can have the superconducting processor, which is basically a junction, like when you do an integrated circuit, you put aluminium oxide, like a sandwich, oxide, and then aluminium again, and then here this junction will have several energies, several energy levels, but the quantum bit will be the manipulation of the two lowest energy levels. We will assign the lowest to a 0 and the first excited state to a 1. That's it. So what I want you to understand is that the assignation of 0 and 1 is not always the same. It will depend on the hardware. For some processors it will be magnetic states. For other processors it will be the energy of an electric device. Okay? But the point is that at the end we still handle 0 and 1, 0 and 1. Okay? Here are some of the quantum processors. I will just name them, and then if there are questions, then we can come back at the end of the talk. So there are the superconducting circuits, which are just junctions in a very low temperatures. Then we have color centers, which are like diamonds with impurities. We have trapped ions, which are basically electromagnetic devices with ions, individual ions, and then we manipulate their energy. Or quantum dots, which account for the presence or the absence of one single electron, so that is 0 and 1. Okay, so now the question is how to understand the quantum bit. We said that the only thing that we know about the quantum bit are the probabilities. That's it, the probabilities, right? So the probabilities will be the important, the key feature to understand the qubits. And then if you go to the literature, you will read a lot the word block sphere. If you see some talks on YouTube or you go to conferences, they will talk extensively about this block sphere. So I want to tell you in simple words what is a block sphere to understand the quantum bit. Basically, you have a physical system. It can be a nuclei, it can be a junction, and then you have two different states. But again, what you know about these states are the probabilities. The probability that you will have this state or this state. That's it. So you will map this model into a sphere, a 3D sphere for one qubit, one quantum bit, and then you will make a convention. For instance, if I put a dot, for instance, this green dot here in the North Pole, it will represent that my quantum bit is prepared in such a way that 100% of the times I get 0. Any point of this parallel will represent that my quantum bit is prepared in such a way that 75% of the times I have 0. If I am any point on the equator, represents a quantum bit that is prepared in such a way that it's 50% that I have 0. If I go to the South Pole, that means that my quantum bit is prepared in such a way that 0% of the times I get 0. Okay? So basically, you can think this block sphere as a mathematical representation of the probabilities. It's like a probability ruler, okay? And it's by slices. Every slice has a different probability associated. So we cannot manipulate the states. What we can manipulate, as we already said, are the probabilities. Then in this block sphere, which is a mathematical representation of this processor, a quantum logic gate has to be understood as the manipulation of this, this point, taking this point to this other point on the sphere. And this translates to basically manipulating, let's say that we start with a quantum bit 100% of the times on 0. And we apply electromagnetic radiation, it can be microwaves, radio frequency, and then at the end of this application of the electromagnetic radiation, poof, your quantum bit will suddenly have 75% probabilities of having 0. So that's what the quantum gates do. It's basically manipulating the probabilities associated to the quantum bit, and that's it. Okay? We don't manipulate the states by themselves, just the probabilities. Okay? For instance, there is a famous gate which is called the Hadamard gate, and it basically takes the North Pole to the equator in this spiral motion, for instance. And at the end of the operation, you will have a qubit that is 50% of the time 0, 50% of the times 1. And then you can say, well, it doesn't sound so... so what's the point of manipulating the probability, you may ask. No? For instance, let's say that we apply that quantum gate, right? In the diagrams of quantum computing, all the gates are little squares. For instance, in the classical ones are like arrow shape, right? Like these vertical and then circle shaped things, right? In quantum computing, they are all squares, and inside you have the letter of the associated gate. In the case of the Hadamard, when it's an H gate, and what it does, so for instance, this is a table that says that the only event is having 0, 100% of the times is 0. Okay? After the gate, we will have a 50-50% quantum bit. So that means that we will have the event 0 or the event 1 with 1/2 probability. And the question is, why is this important? Because if you, for instance, if you work with random numbers, if you go to classical computers, what you get are pseudo random numbers. Okay. Here, as we saw in the words of Bohr, the microscopic world is by nature random. That's why we only describe the probabilities associated. So that's one big advantage, because if we prepare our quantum bit in this manner, then our quantum bit can be a quantum random number generator, a real by nature. Then if I ask this coin, is it 0 or 1, and then I wait, and then I register the measurements, that 0 or that 1, in this case, will be by nature random. So that's one of the advantages, especially in cryptography for the key generation, etc. Right? And it's that this is the simplest algorithm that you can learn. Just apply the Hadamard gate, and then you get a fully random quantum bit, etc. Now the question is, what does it look like, coding in quantum computing? Well, basically it's Python, and after declaring a lot of libraries, etc., basically you create a register, a quantum register, which will be this quantum bit. Then you have to create a classical register. Why? Because you have to, this is the coin on the air, and this is the measurement. You need to keep track of the measurement, was it heads or tails, right? So you need to register the classical one and the quantum. Then you create a circuit, and then you start applying the gates. It's Python, so it's just dots, the name of the gate, and then you put the index of the qubit. Here it's just 1 and 0. And then you apply another block, which is the measurement block, right? And then you draw the circuit, and then you start these lines, which are basically the simulation, and then you will get probabilities. So that's it. So as you can see, it's not very difficult. It's Python, and it's always the same instruction. Is apply a gate to a given qubit. And now the question is, this is one example. It's in Qiskit, but actually, every company has developed their own language to manipulate the quantum processors, because every company develops different processors, so they have different instructions to manipulate the specific processors, right? So you have IBM that has the Qiskit language, you have Google, which has Siri, Microsoft, which has Azure, Rigetti, Xanadu, etc. So there are many different languages. One of the most popular is Qiskit, right? And well, the explanation, we can talk about it at the end. But the important point is that most of them use Python. And the answer to that question, why Python, is because they are companies and they want to sell. And if you want to sell something, you will use the language that everyone knows. And Python is one of the most popular in the society, let's say. So that's why all the companies are developing these languages using Python. Basically, it's just to draw the pool. Now that we saw basically what are the quantum gates. The question is, what is a quantum algorithm? So we have the blocks, and then an algorithm is putting all the blocks together to achieve one purpose. And the question is, how should we understand a quantum algorithm? And the answer to that question, I always like to say to my students, think about a quantum algorithm as a music score. Now it sounds funny, but I will show you that there are more similarities with the musical score with the quantum algorithm than the classical algorithm. In a musical score you have different musical instruments. In the quantum algorithm, the different quantum bits are precisely noted by their name. In the musical score, in a concert, the instruments don't move from their seats. They are always static. In the case of quantum computing, all the quantum bits don't move. And that's very important to understand. I don't like to teach quantum computing with the photon because the photon gives you a false sense that the qubits are moving. The photon is a very special one, but they are there in the chip. They don't move. It's very important to understand that. The quantum bit doesn't never move. In contrast to for instance, in the classical bit, the 0 or 1 can be the current, the electrical current, right? So the electrical current moves. Then the bit moves in the space, right? But here in quantum computing, the quantum bit stays there. Very important. Secondly, the horizontal axis of the music score is a time axis. It gives you a sense of the time. This is first, this is second, and this is third, etc. In the quantum algorithm, it's the same. The horizontal axis is a time axis. This will talk about timing. In the case of the classical algorithm, when you put the AND gate, that's all the horizontal axis is a space axis, because that tells you the terminals of the junctions, where you get the voltages and the currents. But here the axis is a time axis. Here you have the nodes, and these nodes means that this will happen after this one. The same way this gate will happen in time after you have applied these quantum bits. And every one of these nodes will have a time value like 1 or 1/2 or 1/4, right? So in the same way, every one of these quantum gates will have associated a timing, which will be related to a very specific frequency, resonance frequency of the quantum system. Okay, so it's the same. As you can see, the analogy is very good. Well, now that we have understood what is a quantum gate, what is a quantum algorithm, we have also to understand the difference between classical programming and quantum programming. When you teach classical programming, you start teaching a logical language, like types of variables, commands, loops, etc. And the algorithms are nothing more but a way of combining all these words that you have learned. In the case of quantum programming, it's a different mindset, because it's not a way of combining things. One algorithm is one specific strategy to solve one specific situation. And then the pedagogy is based on case studies. So when you open a quantum computing book, you will not start with the command for the command why. No, you will start with situation 1, algorithm 1, situation 2, algorithm 2. There is no order that you have to first learn this algorithm and then this algorithm and then this algorithm. It will depend on your needs. If you say I have this situation, then you will have to go to this algorithm. Okay? One case, one algorithm. It's very important.
Sorry, do you have to program only in Python, or are there other programs?
Yes, there are other languages. other programs. I mainly specialized on Python, but yes, there are others. But it will depend on the companies.
Okay.
Basically, because all those companies provide a cloud service. Then you connect to the cloud and you run the program. And the most famous ones are Python, basically. At least the free ones, let's say, the ones that we don't need to pay at the beginning. Right?
Okay. Thank you.
Yes. So let's see. We will see. Well, we cannot see it over there, but we will see two algorithms, the most famous ones: the Grover algorithm and the Shor algorithm. Those will be the ones that you will hear everywhere. Let's start with the Grover. Case of study: database. So imagine you work in a company. There is something called logistics, and then you have a supply chain. Basically, you have many stages. You have the raw material, which can be plastic, aluminum, glass, etc. Then you have a factory. You take these materials to a specific factory. Then the byproduct, you will take it to an assembly facility, and then you will distribute the final product into some customer store. Okay? And then the question in logistics is finding the optimal path that will cost the less money and will grant me the most money. Well, this is a cartoon, but in real life there are thousands of possibilities, and it grows exponentially. Let's say that this is the optimal path among all the paths. Basically, this problem is the kind of problem that the Grover algorithm will deal, right? So we have a lot of possibilities, and then we will pick the optimal one, or the one that we are interested in. So the question is, okay, how do you treat these kind of problems? Another problem is in biology. That was in logistics, there is another one in biology. In biology, you have, for instance, cells that can get cancer or not, can die or can survive. And this surviving or death of the cells will be described by Boolean relations. The more complex the biological network is, the bigger the database will be. There will be a exponential growth in the possibilities. And these possibilities, the search for the optimal one, let's say that we are interested in finding the case when my cell in the brain, which is the cortex, it's a cortex model, will survive. Then in that case, people are doing research. This was relatively recent, 2 years ago, and this group basically made a quantum algorithm to search for the optimal situation in which the brain cell will survive. So we have many different types of situations for searching problems, okay? But aside the nature of the problem, let's imagine, just to fix ideas, that we have a database. It really doesn't matter the meaning of scenarios. Let's just imagine that there are 4 scenarios. It can be a cell, it can be the money in the company's view. Doesn't matter. Let's imagine that there are 4, and then in order to treat this problem in quantum computing, first you have to translate this problem into a binary problem, because we need zeros and ones. So there are 4 scenarios, then we will use 2 bits, 2 quantum bits, and then we will have scenario 1 associated with 0, 0, scenario 2 to 0, 1, scenario 3 to 1, 0, scenario 4 to 1, 1. And let's imagine that we want to find that the scenario 4, the register 1, 1, is the item that we want to find. Right? Then how do we do it? First, we have to use the Hadamard gates, because there are 4 scenarios. So we have to consider simultaneously all 4 scenarios. So for that, basically, we will consider 2 quantum bits, which are 2 points on the air. Then we have heads or tails. So we have 0, 0, 0, 1, 1, 0, da da da, right? And we will manipulate, this is the, doesn't matter, this one. Then for the first qubit, we will apply the Hadamard gate, and for the second qubit, we will apply the Hadamard gate. The Hadamard gate will will equalize the probabilities. So at the end of this, so when we start with a reset register 0, 0. After the first Hadamard gate, it will be equally randomized. So then we will have for the first bit 0 and 1. So the second bit will be 0, but the first one will be either 0 or 1 with 50% probability. Then we apply another Hadamard gate, and this Hadamard gate will equally randomize the second bit, and then this second bit will be, so in this case we will have 0, 0 or 0, 1, and then here we have 1, 0 or 1, 1 with 50% probability. So we will have 50% times 50% is 25%, right? What does that mean? That at the end of these Hadamard gates, we will have the 4 registers equally random. And that's very important because it's like putting on the same ground all the scenario, all the items on my truth table. And then we will start manipulate everything, and since they are all equally random, we are simultaneously operating on the probabilities of all the items. Okay? And then we will start, well, because of time I will not get into details, but there will be some gates that will mark with a minus the item that we want. We will get negations, etc. And then by the end of our algorithm, we measure, we send all the results in the classical registers, and then we compute the histogram and the path. There is a peak on probability in the item that we are interested in. Now this is trivial for 4 items, but imagine you have 1 million. And you will have like negligible probabilities, and suddenly path 1 peak. And then that peak will be the item that we are searching. For instance, let's imagine another example. Imagine that you have a phone book. You have names, and then you have phone numbers, right? So this is the first part of the database is ordered by name, A, B, C, D, etc. But the second part is not ordered, because the 0, 0 should be the first one, but it's not. So the first half is ordered, the second half is not ordered. So what we do in quantum computing is translating this in a table of zeros and ones. It really doesn't matter, but here in this case you need 8 quantum bits. You have, instead of names and phone numbers, you have a table of zeros and ones. And then you start doing the same. Here you can see that we have the Hadamard gates because we are going to put at the same level all the items of the truth table, and then we will operate. And imagine, that David and Penelope give you a phone call. So you just know that the 33 called you and the 02 called you, but you don't know the names. Then with the numbers, you have to go here and then you have to start searching, right? So you have, classically you say, oh, Alex, what number is it? No, it's not a number. Brandon, what number is it? Etc. But quantumly, we apply this Grover algorithm. This is one example that we worked with my students. We have this, and then you clearly have 2 peaks. And then you say, okay, 2 peaks, and then you will see what register they correspond. You say, okay, this part is obvious that will appear because that's the phone number, that's the marking item, that's the part that I marked. So it's obviously that there will be a peak. But I'm not interested in this, I'm interested in the first part of the register. So this first part will tell me the name. So 0011, that's 3, that means that it's the 4th item. So if you go here, it's 1, 2, 3, 4. Then David was the one who called. Okay? and so on and so forth. Now, let's go to a second example, and then I hope I won't run out of time. But that's it. That's one application of two applications of the Grover algorithm. Now, a second algorithm is the short algorithm, and then in this case, it's about cryptography. So, does anyone know the RSA protocol? No? Raise your hand, you know it? Just one? Two? The others? No? No? Okay, but then you have homework, okay? There is a paper. You can notes, you can write down. So, long story short, there is a way to send and receive information, which is called the RSA algorithm, which stands for the names of the three people that introduced it. You can copy it. I know you are far more intelligent in computing than this. You can search it. But the point is the following. In a very schematic way, you have a sender and a receiver. You have three integers. The public key will be two integers e and, let's say 755, and then you have a private key. This will be to send information, this will be to open information. Then let's say that you want to send a message, which is the letter N, which you will assign the integer 12. And then you will use these two integers to encrypt this value 12 into some encryption C. Then you get a modular equation. And then the result is that this C will be 23. 23 is the letter X, so you send the letter X. Then the receiver will receive the letter X, and then he will solve again a modular equation using the private key, which are the two integers, and then the residue will be 12. And, oh surprise, it's the same method. It's just that. But the point is that the private, in order to hack this RSA algorithm, basically you need to know one integer, which is D, right? Because the N is common between the public and the private. So the point is that in order to get this D, at some point you have to decompose some integer into prime factors. That's the whole point. And now this is very important because when I give you two numbers, for instance, 3 times 5, how much is it? 15. Okay, 15. But if I give you 21, how much? What are the prime factors of 21? Don't worry, take your time. 3 and 7. Exactly. But if I give you this prime number, this number, and I ask you for your prime factors, that's another thing, right? Multiplying it's easy, decomposing it's not that easy. And precisely that's the whole strength of the RSA, that the bigger the number, the hardest to get the prime factors. That's what is basically based on the RSA. And what they do is just increasing the size of the number. Good. Aha. So the goal of the shorts algorithm is not to find the prime factors, because there is a common misconception that says, oh yeah, the short algorithm is to find the prime factors. No, it is not. There is already a classical algorithm in order to find the prime factors. It's very well known in number theory and mathematics. But there is one tiny step that takes a lot of time. And that tiny step is what the short algorithm solves. It's finding an integer in which the prime factors, from which the prime factors of another integer could be deduced. We will see some slides later. So, see, even the fly is interested in something. So you will start, we will see the classical algorithm. But basically, this classical algorithm is based on the following. You take an integer, let's say a equals to 2, and then you will compute the many different powers, 2 to the power 0, 2 to the power 1, 2 to the power 2, You will have the number that you want to decompose prime factors, and then you will find the residue, right? So, and then you will plot the residue. Since it's a modular situation, it will be repeating because you increase, and then you divide, and then you will get the lowest residue. Okay. For this case, the period is very easy. It's here, it's 6. Every 6 units it will repeat. But the bigger the number, the period, it's harder to find that period. It's very important. Now this is a classical algorithm. 6 steps. First, let's say that you want to factorize to find the prime numbers of 21. Then you choose an integer, let's say 2. That integer must be a coprime of the number that you want to compose. Okay, so check. Then you have to find that period. That's why this chosen 2. We compute the different powers, then we get this residue plot. We find that the period is 6. And then, and this 6 must satisfy this equation, okay? Just like that. And then, when you get this 6, you have to compute the great common divisor between this a to the power r divided by 2 plus 1, and then minus 1. And then, here, this algorithm for finding the great common divisor, you learn it in secondary school, primary school, so it's straightforward. Okay? The difficult part is basically finding this. Anyhow, so you get this, so it's 2 to the power 6 half, that's 2 to the power of 3, etc. And then you get 8 plus 1 is 9. The great common divisor between 9 and 21 is 3. The same for this case, 7 and 21, then 7. Then you get 3 and 7, that's it. Then let's say that you want 25, no 15, sorry. And then you choose the a to be 4, and then you get this plot, here the integer is 2. And then, in order to find that specific integer, that r, this is the short algorithm. So again, here are the Hadamard gates at the beginning. That means that we will consider all possible scenarios. Why? Because we want to consider all possible scenarios. Okay? And then you will manipulate all the probabilities. At the end, you get 2 peaks of probabilities. This peak always appears. You have to focus on this peak, which is 1 and 0. Who can tell me what's the decimal of 1 and 0? What decimal number is 1 and 0? 2. Good. Then it's 2. Then that means in our classical algorithm, this r equals to 2 is what is found in the short algorithm. The short algorithm doesn't decompose in prime factors. The classical algorithm is the one that is used to decompose. The short algorithm just gives you that modular period. And then again, you apply the classical algorithm. You get 4. 4 plus 1 is 5. 4 minus 1 is 3. The great common divisor between 5 and 15 is 5. The great common divisor between 3 and 15 is 3. There you have it. And then you say, but that's 15, that's 21. Actually, that factorization, this short algorithm to factorize 15 was the article in 2000, in the year 2000 that implemented the short algorithm in a real quantum computer. And then they published it, and the media mocked that result. They say, result of the millennium, 15 equals to 3 times 5. But what the media didn't understand, it's not about 15 is equals to 3 times 5. It's that once we can perform this in a real quantum computer, if I have this number, it doesn't matter. We just need to apply this in cascades, and then you get it. That's the whole point. It's not about 15. It's about the possibility of implementing that algorithm. Okay, so conclusion. Basically, we start understanding that a quantum bit still have 0 and 1, but we just manipulate probabilities. It's a coin on the air. The quantum gate will manipulate these probabilities, so we go from one probability to another probability of this quantum gate. And we saw that these quantum gates can be assembled in a quantum algorithm, which is the same logic as a musical score. And we saw that there are many quantum algorithms which are focused on search problems. And we saw very briefly two of the main search problems: a database search, which is the Grover, and a period finding search, which is the short algorithm. And most importantly, there is, because many people say, quantum computing will replace classical computing. No. There is always a classical algorithm that works, and there is always one step that takes a lot of time. And usually the quantum algorithm will give the output of this time-consuming step. That's it. Okay, so no, quantum computing will not replace it. It will take charge where the classical computing takes a lot of time. Okay. And well, I show you a little bit. I'm doing my postdoc Automático control, and there we have a quantum computer of 2 qubits. These are the students, you see, they look happy, so it's true. Quantum makes happy people. This is a magnetic resonance, nuclear magnetic resonance machine. Basically, here are the magnets. Here is all the instrumentation, and inside there is a liquid with 2 qubits that we manipulate the nuclear. And then we get all these histograms, etc. Okay, so thank you for your attention.
Okay, thank you very much. Are there some questions?
En español.
Bueno, yo me preguntaba cómo resuelven el problema de las perturbaciones. O sea, tú tienes tu qubit y tienes varios, y pues entre ellos están interactuando en el campo cuántico y todas esas partículas virtuales que salen en los diagramas de Feynman. Entonces, ¿cómo no resuelven? ¿Por qué no interactúan entre ellos y cambien sus valores?
Okay, so in that case, basically, yes, quantum systems are very sensitive to perturbations, especially, for instance, in this case you have room temperature, so it's quite high, the temperature for the microscopic system, and actually there is no problem, because with those perturbations will have an exponential decay, and the only thing that we have that is done in the hardware is to take into account that perturbation, so it's already estimated. Now the other question, which I think is closer to your branch, is error correction. That you have, I don't know, this algorithm, and then you say, what about if the bit flips in this stage, what do I do? It's very similar to the classical concept. We will have ancillary bits, and then we will have extra gates to compensate for an eventual flipping of the qubits. So it's the same. For the hardware, it's already everything is taken into account. So that's no problem. For the coding, there are also strategies. There is a whole area which is called quantum error correction. And again, it's how many ancillary qubits you need, what kind of gates or conditional gates you need to correct an eventual flipping, etc. And of course, there are more reliable processors. For instance, the ones that are very famous is the superconducting, because you cool the temperature down to millikelvin. close to the absolute zero, very close. So, because you cool down, the perturbations remain very, very low. So that's like one of the most reliable, let's say, with not so many noise. Okay, not so much noise. But all of this, you can buy it. So this is from the 90s. That's precisely why a little bit giving the talk, because it gives us a sensation that quantum computing is something of science fiction, right? Like Interstellar, Ant-Man, superheroes. But actually, all the processors were already built on the 90s. That's why there are companies, and they sell them. And there is actually one company here in Santa Fe, a Chinese one, that sells these quantum computers from magnetic resonance with these ones. So there is a vast number of companies that sells that. Universe for superconducting ones, etc.
Any more questions?
You need to know all the scenarios and the answer, no? Before applying.
That's a good question. Yeah, so you have a database. You have to load the database. Let's say that, for instance, imagine you have a drone, flying drone, and then you want to measure the signal, because you don't want to miss all the news, right? So you want to make sure that the signal for your cell phone will be okay in all the area. So you fly your drone, and then your drone will start acquiring data. And then the drone will say, position A, power of the signal, path. Position B, power of the signal, path. Then you start acquiring data points, and then you will have 1 million. So you have already the database. But you need still to search what is the point that has, I don't know, or maybe the trajectory where you have 1 megawatt, I don't know, some kind of power. Then you already know the marked item, you know the power that you want. You say 1 watt or 1 megawatt. Then you will start marking, you will tell these are like the marker gates. So you will say, I will mark every time I have 1 watt in the second part of the register. And then you will get this kind of peaks. And then you will say, let's say that this part means 1 megawatt. And this part also 1 megawatt. But here will tell you the position. You will start saying, okay, this is the position that has 1 megawatt, this other position has also 1 megawatt, and then you can reconstruct a trajectory. Okay. So, because yeah, it sounds like tricky, because it's like I will find the answer of the question that I already know the answer. But no, because you have the data, but it's not sorted out. It's just the raw data, and you want to get one specific situation, right? He doesn't know solid state, but he knows how to do the click, click, click. Right? I know the click, click, click. Basically, the complexity here refers to the number of stages that you will apply the gates in a logical way. Now, regarding the time, well, there are tables in which every gate will have associated a given time. And it will depend on your processor, right? So maybe your processor of superconducting is very fast, maybe it's nanoseconds, and then the time here from 1 square is tens of nanoseconds. Then you start adding, and you will say, okay, my algorithm will last 100 nanoseconds. And then depending on your processor and your gate, then the time will vary. but the most important part is that even though it might seem that it takes a lot of time, for instance in the RSA, something that a supercomputer can take, something that a supercomputer can take 10 years to factorize, is a short algorithm can do it in maybe 1 month, 1 day. So yes, it's quantum mechanically speaking, it's very large, but it's smaller than the classical version.
And in your platform here in the laboratory, in the Automatic Control laboratory, how many qubits you may simulate?
Okay, that's an interesting question. So we have 2 processors. This one, which is a solenoid, is like this size, 2, is for training engineers because they don't know quantum mechanics. That's the whole challenge that well, I have trained already 2 generations of students in 4 months from 0 to 100 in quantum computing. And this processor is for training them into the hardware. There is just 1 qubit, 1 quantum bit, which is water. In the water you manipulate a hydrogen nucleus, so it's just 1 nucleus. And then you start learning how to acquire the data signals, how to interpret, etc. This one, which is properly a quantum computer, has 2 qubits, 2 real qubits, very important. So you can do a variety of problems even with 2 qubits. It might seem like, no, I need like 100 qubits. But it will depend on your problem. Like, I will go very beginning. But for instance, with 1 qubit, you can already do many interesting things. For instance, here you have a quantum random number generator, which is essentially cryptography. It's 1 qubit, you see, so it's not a question of how many qubits, it's a question of what problem do you want to address. With 2 qubits you can do a variety of problems, and then another advantage, because it doesn't sound very appealing, just 2 qubits, one of the advantages is that this computer comes along with a simulator of 18 qubits. And what's the big deal if it's free? I can connect to the cloud of IBM, etc. Well, one advantage is that you don't rely on, if many people is using the IBM platform, you have your local cloud, and you can say, okay, all the students or researchers in the department can connect to the local cloud to use the simulator. It's like a private cloud. That's one. So yeah, in this case we can do this simulator, and then you say, but at the end I want, let's say, 8 qubits, and I want to do a simulation because I want to report it for a paper. And then you said, here is just a simulator, but it's very important, the simulator, because once you are sure that this simulator works, then you send it to the cloud of IBM, because IBM has 2 clouds, the real experiment and the simulator, the simulation. Usually, you have to take a lot of time in the simulator because you have to debug the algorithm. Very, very clean. You have to find, because you can reduce gates. Maybe you use 5, but maybe 3 are redundant, and then you have to find something. Once you clean your algorithm, then you send it to the cloud of IBM, and they will charge you by time of execution. But that's why it's very important to clean it. But if you are rich, then you can send it, and then you can get a huge bill, and it's okay. Now, you say, I want, this has the simulator of 18 qubits. 18 qubits, and then you have the 2 qubits. And both of them, you can connect them to a local cloud. The experiment of 2 qubits and the other. And then you say, okay, I want a cloud with 5 or 20 real qubits. What do? This company also sells a superconducting one with all the refrigerator and all the instrumentation, etc. And the seller told me they have 20 real qubits. So in this sense, for instance, the computation, well, that's what the seller said, but we have to check. You could, for instance, buy it, and then the computation department can offer the cloud to the Cinvestav, 20 qubits, for instance. And then it becomes like the cloud managed by computation, for instance.
And which company has the cloud?
Yeah, so these quantum computers is called SpinQ. SpinQ is S-P-I-N-Q. And it's they are right here in Santa Fe.
And are you aware of the quantum computer in the engineering faculty in UNAM?
Yes, actually everyone asked us about that, and they got the model behind us, because that's what the seller said. They told us, it's good that you bought this model because this is the newest one, and UNAM bought the model before this was on the market. So we have the newest one compared to UNAM.
Okay.
But it's the same. The only difference is that here you can have access to the signals, and because this is the control department, they are interested in putting in the control signals, and this is more transparent. The other one is like a microwave where you do the click and you get the results in that sense. But here you can, for instance, you can put the oscilloscopes here and get the signal, or even put another signal. That's why it's called a Gemini lab, because it's like a mini lab. It's for training, like a high training. But you could, for instance, yeah, you could hire me. I'm unemployed. You could hire me, and then I can tell you that this quantum computer of SpinQ, the superconducting one, could offer like a cloud to the Cinvestav, and it costs 20 million pesos, which sounds a lot, but in the market it's the cheapest one, and you don't pay the supplier because it's right here on the side.
Okay, thank you. Are there any more questions? So let's thank again the speaker. Thank you very much. I give you a recommendation for the talk. Thank you very much for the talk.